Introducing Local Foods for OneHacks, a simple service that allows farmers to post their items on their personal website. First, the user is prompted to log in using their local foods account. Then the user send an email verification code. This is achieved using Twilio SendGrid. If the user is new, their data is then stored on CockroachDB. The farmer can add a new item to his shop. The farmer is required to post both an image of the leaf and the vegetable. The farmer can then run a health diagnostics check to see whether his fruit or vegetable is healthy and good looking to post for the public. Moving on to how we trained our machine learning model and built our neural network from scratch.
So we have two models for this project, and we get the data sources for the training data from Kaggle. And on the right, we can see a word cloud of the possible types of diseases that the leaf might have. And on the left, we see the amount of training samples we have for each one of these, and we have roughly 1,500 to 1,000 for each one of these diseases. On the left, we can see that the proportion of the training samples to the total are roughly the same. And this shows that the training won't be skewed. On the right, we have images of the leaves and the diseases they might have or they're healthy, and they're included in the title. And we can see the types of fruits we have, and on the bottom we have the augmented version of the top fruits. And we use these augmented versions to expand the amount of training samples we have, so we have more training samples for our model. This is a key aspect of our project, as we only have 107,000 parameters, and most models have over 60 million parameters for such a complex task. And we use the squeeze net outlined by the Berkeley paper. And the fire module is found in the squeeze net, where we squeeze and expand our representation. We squeeze the representation of the image, and we expand it out using 1x1 and 3x3 convolution filters. And you can see the model architecture. We're squeezing and we're expanding it out, and we're concatenating that output, and we're pooling that. And on the right, we see an image of the TensorBoard graph. And I use TensorBoard a lot through this project to debug my TensorFlow model, especially as I was running through many problems, especially since the amount of parameters were very low, and I had to experiment with many different types of optimizers. And I finally came up with RMS prop to quickly get to the saddle point of a loss function, like the global minimum of a loss function. And on the right over here, we have a piece of code. So there wasn't any implementation that the paper gave, so I had to use the paper and the TensorFlow API to create code to implement this model. So there's something called the fire module that outlined the paper. And as I said, there's the squeeze and expand. So I have a method for both of them. And we're expanding, we're squeezing, and we're expanding that out, and we're concatenating that input. And we can see a convolution, the pooling, and then the fire modules to create our model. So this is a picture of our model results on a couple of images. The green ones are the ones that the model detected accurately, and the red ones are the ones that they did not detect accurately. All of this code is generated through the Collab notebook that's on DevPost. So if you want, you could run the code again. You can see the display. The code for all of these displays are included in this Collab repository, and the last image was created on this code block. And if the prediction is equal to the actual label, we would keep the colors green, otherwise we'd keep it as color red.